In Figure 1, we see a typical layout of facilities within a customer's yard. We have chain link fence, underground water pipes, and the underground secondary service. You will notice that we show an earth ground at the customer's meter base and at the pad mount transformer. These grounds may be solidly connected to the underground water pipes and perhaps even to the chain link fence. In Figure 2, we see an ideal pattern of fault drain within the soil. The X shows the point of the faulted conductor. From the point of the fault, dashed lines indicate the path of the current flowing from the fault to the pad mount transformer ground rod. This pattern looks somewhat like a football in its shape, and indeed this is what you would find if we did not have other things in the soil, such as the grounded water pipes and fence, which draw off some of the current flowing between the point of the fault and the pad mount transformer. Bear this in mind and then turn to Figure 3, which shows Figure 1 slightly modified. Here is typically how the facilities in the yard affect the pattern of the current throughout the soil. See some lines of flow going over to the chain link fence, some to the meter base ground, and some to the water pipes, and we refer to these as leakages to nearby neutral returns. These leakages are generally lower in their magnitude than those flowing back to the transformer, and they normally result in lower readings on the instrument. You will notice I show a wandering trail, sort of squiggly line, from the fault to the transformer. This happens when you have a highly conductive path within the soil, such as a vein of clay running through the yard. And, indeed, the readings you take may lead you along that line and sort of wander back to the pad mount or over to the point of the fault. Let's look at Figure 4 now and discuss the method for taking readings with the instrument. Here we represent the fault pattern a little differently, remembering that in the other diagrams we spoke of the dashed lines as representing the current flowing in the soil. Now in Figure 4 we can think of the dashed lines as being the voltage pattern that results in the soil due to that current flow. Now you see we have an area that I've labeled the transformer zone on the left and the fault zone on the right. Let's say that you set up your probes perhaps as shown in position number 1. Not knowing the exact path of the cable, but just by judgment, you start somewhere near the general path of the cable and assume for the moment you started in the position number 1. At that point you would have gotten a fairly low reading on the scale. Now, leaving one of the probes fixed, let's say the one in your right hand, move the other one around at approximately 45 degrees from your original reading position, and this would put you in position number 2. At this point, you should see an increase in the reading on your scale. With that, then, you would come into position number 3 and see still another increase. Now, if you move your probes in football chain fashion along the line as directed by the position of maximum reading, in this case, position number 3, you will continue to get higher readings all the way to the fault. As you move towards the fault, you will have to turn the scale adjust knob counterclockwise in order to keep the needle from staying solidly at the right side of the scale. In other words, you will have to adjust the needle back on scale in order to continue getting relative readings. If you selected the proper direction when you began to move your position, then you will get higher readings as you go. However, if you select the wrong direction, then your readings would show lower values than what you had in position 3. So it may be that you'll make 1 or 2 moves of the instrument before you determine which direction you should move to go toward the fault. Again, as you went from position 3 to 4, you would have gotten an increase in reading, and so on until you arrive at 5 on the drawing. At this point, you will see a change in readings, and as you pass one of the probes across the fault, you will see the readings begin to drop. In fact, when you are standing directly above the fault with each probe equally distant from the fault point, then you will get a 0 reading on the meter. To understand why we get a 0 at this point, we just realize that the voltage patterns are in the shape of circles around the fault, and when we get both probe tips on the same circle, then there is no voltage difference to read. So it is this zero reading position that we are looking for. One of the things we found is that certainly we have the pattern from the point of the fault, but we also have a similar pattern existing at the transformer, since the currents are flowing to it as the other point of the earth circuit. So we can get readings in the transformer zone similar to what we get in the fault zone. What we have learned as a matter of practice is you do not usually need to know the exact path of the cable. The transformer and service locations are known, and where you want to try to get readings without first scoping the cable, what we have done is to go approximately 2/3 the distance from the transformer to the service, be that a street light or a customer's meter base. There we start taking our readings. In other words, we go beyond the halfway mark between the transformer and the service in an effort to get into the fault zone. It is possible that if you stop short of the halfway mark that you will get your higher readings as you move toward the transformer, because remember, most all of the current lines leaving the fault are flowing to the neutral at the transformer, causing a concentration of voltage gradients at the transformer just as they are at the point of the fault. So we have to be a little careful of how we work the instrument and in interpreting what we have as indications. Briefly then, we can restate the procedure as follows. Number 1, select a point about 2/3 the distance from the transformer to the service. Number 2, begin taking readings and determine the general direction of the fault. Number 3, move along this line in the direction that gives increasing readings. Number 4, continue until you reach the point of the fault, which as you pass over it will cause your meter reading to drop sharply, and as you get the probes at equal distances on each side of the fault, you will get a reading of 0 on the instrument. We don't say we can get every problem solved with this instrument. What we do feel is that over 90% of the problems can be found faster, saving time and frustration on the part of the people in finding and digging these things up to make repairs. I want to thank you for using this instrument, and I sincerely hope it serves your purpose well.